It's an absolute delight to be here. So I guess I am an assistant professor in the School of Physics at Georgia Tech. So I guess I was going to tell you a little bit about sort of myself, my path to where I am, which is not completely standard, I guess. I mean, I guess, well, we'll see. And tell you a little bit about some of the projects I've done throughout my career. Um, so to start with, so I was born in Berkeley, California, and my parents, I guess, are both scientists. My dad, Sabetta Matsumoto, is an organic chemist, and my mom, Dita Soma, was a geologist. So not surprising that I also ended up in science. But I also want to point out that my mom has always been like a textiles person and does a lot of like textile art. So I grew up doing that. So that's a big thing that has shaped my current path. And I guess here's me when I was a little baby. This is at the Monterey Bay Aquarium in Monterey, California. So I do come from kind of a long line of scientists. This is my mom's father. He was an organic chemist and taught at Columbia College of Pharmacy. And then this is my dad's mom, Lillian Matsumoto, and she has some very amazing stories about World War II and the Japanese internment in the US. So ask me about that later if you're interested. So this is from my high school. Jim Hogan was my high school chemistry teacher, and Jonathan Briggs was my high school physics teacher, and they very much encouraged me in science. Like they were, I think, my two favorite classes. And I guess at the time, my goal was to be a surgeon. I really wanted to be a doctor. And so that's, I guess that's sort of why chemistry was important to me. And then that was my goal when I went to college. And so when I went to college, I ended up with a sort of started out with a biochemistry degree. And for me, that was sort of okay for the first little bit. I had a job working in a cancer lab, and the research was really, really fascinating. We were sort of looking at ways of coming up with like an optical way of diagnosing leukemia, based on sort of fluorescence microscopy, where you can't do like scans for leukemia and see solid tumors. And then one day I showed up and we had to kill mice, and I quit on the spot. So I needed a new job, so I went to the physics department, and like physics was my favorite course at the time. And I ended up taking a job with a group working with CERN as well. So I guess here's me as a CERN summer student. So I can confirm that what Masahiro said, that everything, I guess this was 20 years ago, that everything you said is exactly what I experienced too. And so that was quite quite fascinating. I didn't work on Alice. This is transition. Oh gosh, I can't even remember. It was TRT. I can't remember what it stood for as part of the experiment we were working on. And then I guess after that, I took some classes in the physics department and ended up receiving a fellowship that I had to do that would pay for school, which in the US we have to pay for a lot of our schools. So this was paid for things, but I also had to get a master's degree. So I ended up doing that, and I worked with Professor Randall Kimian, working, and his research is in soft matter and liquid crystals. And so that kind of set a lot of what I'm sort of spent the rest of my time doing. And I really liked that so much that I stayed on to do my PhD in the same topic. But while I was there, I really developed the hobby of knitting. So this is like a sort of wall hanging that I made when I was a student. And as a student, so these are actually the slides I had as a student. So you can see that everything's changed a lot in style. So the project that I worked on was very much sort of a combination of what Leonel Sensei and Yuan Sensei had talked to us about earlier in the winter school. So we were looking at sort of analogies between magnetic systems and liquid crystal systems. So one of the systems we studied is, we call them sort of chiral symmetric liquid crystals. So there are systems that want to have layers, but they also have like an intrinsic chirality. And there's a very nice analogy with superconductors. And so superconductors have this sort of phase transition where like at a high temperature and magnetic field, you have like a normal metal. And as you drop the temperature, you get this thing that's called the Meissner effect, where you don't have any magnetic field inside your material. But for some different types of superconductors, there's this intermediate phase where you have these topological defects that form, and these are flux vortices. So you get these points throughout the system. And so quantum units of magnetic field can penetrate the material at these points. So in our system, we have a sort of similar thing where instead of magnetic field, we're looking at tuning the chirality of the material. So at high chiralities, we have like a cholesteric system. So this is like a pneumatic, but it has a lot of helical twist in it. So this is places where I guess Yuan Sensei mentioned things like blue phases and things like that form in this type of material. And then at very low temperatures, we have like this perfect, and low chiralities, we have this sort of perfectly even layered system. But then we also have this sort of intermediate phase where we want to have some places where chirality is able to like pierce through our perfectly layered system. And it does that again with topological defects. And these are sort of helicoids that end up sort of poking through the system. So you get lattices of helicoids forming. And so what someone found was they found this interesting phase that at the time was called the B4 phase. I don't know if it has changed since then. This is quite a while ago. That has these really interesting structures. So there are these twisted helical bundles. You can see that there are lots of layers. The layers are something like 10, 12 nanometers each. And then the periodicity of the twist is something like 180 nanometers, I believe. And one thing that's really interesting about this, and I think is relevant to, I think, the presentation that Sam was talking about yesterday, is that this is a really weird material where it forms and it sort of spontaneously breaks symmetry and can generate left-handed or right-handed chiral phases. But one of the really strange things about this is that the homochiral phase, like the phase that has one-handedness, is enormous compared to the rest of the system. So you get domains that are something like 100 microns. So that is like, I guess if this is 100 nanometers, that's what, 3 orders of magnitude or 6 orders? I can't remember off the top, I can't do math off the top of my head, but something like 3 or 6 orders of magnitude larger, which is really interesting for this phase formation. So that was fascinating. I don't know if anyone studied this, but that's an interesting question for those of you out there interested in these things. So we wrote down a theory for sort of explaining how you can form these sort of coherently aligned bundles of helical filaments. So this is also the helical nanofilament phase, is what it's also called. And if we want to continue our analogy with magnetic systems, basically what we can sort of do is say that if we were looking at these sort of like almost sort of skyrmion lattice type things, we have a range of effect over which like you have like there's sort of a thickness to the skyrmion layer, and then it's sort of a regular phase, and then you've got your skyrmion and sort of regular phase and skyrmion. And then if you get really highly chiral, this this width overtakes the place where you have a normal phase. And so those lattices would overlap. And so we find that there's a critical point where that becomes unstable. And if we make our analogy again with magnetic systems, this phase, we can predict that sort of where it appears on our phase diagram. And for us, we call this the helical nanofilament. Sorry, this is the helical nanofilament phase, and this is equivalent to the A phase in helium magnets. And so like what you see in our system, you end up with these lattices of skyrmions here. So this is sort of this place where you get a competition between something that's very highly chiral and something that wants to suppress chirality. And so that's happening kind of in both systems. So then after that, I did a couple of postdocs. One was at the Princeton Center for Theoretical Sciences, and then the other was at Harvard in the applied math group in their engineering department. And so I'll just talk a little bit about the project I worked on at Harvard, because for me, this was like the first time that I did something that was like really interdisciplinary and then really collaborative in a like a very natural way. So I sort of came from this liquid crystal theory background, and I was working closely with Sydney Gladman, and she is a material scientist. And so what they had done is created a system for making 3D printed materials that sort of fold up into specific shapes. And this was based on this biological process called hygroscopic motion. So this is a pine cone, and we start out in this is a dry phase, and they're going to increase the humidity in the room or in the chamber, and the pine cone closes up, and then as it dries out, it opens again. So this makes a lot of sense for like how something would disperse seeds. Like when it's on the tree, it's closed, and then when it falls off the tree and hopefully moves away from its parent, it opens up and can release the seeds. But what really happens inside this is that you have a lot of collagen fiber, or not collagen, cellulose fibers, and the cellulose is really stiff, but the matrix it's in is soft. And that means that when it gets humidified, it can swell transverse to the direction of its length. So if its cellulose fibrils are arranged this way, it can swell in a transverse direction. And so based on the orientation of these fibrils, you have some oriented in this direction and some oriented into the board. So the ones at the bottom can extend in this direction, and that causes it to swell up and close when it is humidified. And we have similar behavior of different types of plants. So this is a really effective method for distributing seeds in a bunch of different ecosystems. So we decided to make, or I guess Sydney decided to make some ink that was based on this. And so the way this works is when you extrude the ink, the cellulose fibrils align, so you can kind of control the direction of swelling. And so we basically print the ink however we want, we cross-link it, and then once it's cross-linked, we can put it in water and it'll swell in the sort of direction opposite to how we printed it. And so based on this, we can encode different types of curvature. So based on the same concept of the pine cone, we can sort of do an orthogonal set of patterns, and that'll cause it to swell in the top in one direction and the bottom the other way. And so that makes a shape like a Pringle. And we can make different structures. So here we have that orthogonal structure oriented along an axis, and like the pine cone, it's going to kind of roll up on that axis. But the thing that's quite interesting is if you orient it at a 45-degree angle to the axis, you can induce chirality. So this ends up rolling up into a twisted structure. And then we can use these to model different kinds of flowers. So here's one based on the orthogonal orientation. Here's one that's based on the chiral orientation. And so you can see these sort of swelling up and adopting whatever structure you like. And so to prove that we can kind of control things locally, we made this really complicated flower that has, I guess, chiral portions up here. It has orthogonal portions here, and then a more complicated behavior along the bottom. So we're able to capture that through this 3D printing. So then when I went to Georgia Tech, I guess I was able to start my own research group. And I guess one thing that happened when I was a grad student, one of my office mates was studying this thing, it was called the hyperbolic plane. And at the time, I didn't really know what it was, so I looked it up on Google. And like one of the first things that I found was that people were crocheting it. And I was like, whoa, this like blew my mind because the like the thing that was my hobby, like fabrics, ended up like having a relation to science and math, which is like the areas that I studied and really loved. So I basically knew that like when I was able to choose what I wanted to do, I really wanted to blend those things because I was like, well, for me, like I have all of the experience in both, and I feel like no one else is gonna do this. So it was like something that was really exciting for me. So I started my research group in this. And these are some of the lovely students who passed and postdocs that passed through the lab. I think these are the ones whose research, I guess, shows up in some of the slides that I have. So I have a bunch of, I have sort of a little bit on our main project and then a couple of side projects too that I will get to if I have time and not if I don't. But I've just found that working with all of these people, I guess I should go. This is Krishna Singhal. She is now a postdoc at Rice University. This is Shashank Markande, who now actually he just got a new job and I don't remember the name of his company. So he's in data science and is working in the, I think, medical data field right now. This is Alexander Fashin, who is a grad student in my lab who you may have met last year when he was here at the winter school. This is Sarah Gonzalez, who does a lot of simulations for me. She worked very closely with Mike Dimitriev, who's now an assistant professor at Texas A&M. This is Brian Day, who again, you may have met if you were around SKCM² for a long time. He worked a lot on the virtual reality outreach programs that we see around at a lot of events. This is Lewis Campbell, who is an undergrad who was in our lab, who now went to Cornell in the Fashion Institute or research program there, and is sort of doing computational fashion. And lastly, this is Claudia Nardone, who you probably also met if you were at the winter school last year. She's in computation and is sort of interested in finite element simulation. So these are people who make my life coming into work very happy. This is, sometimes being, jobs will get you down, but seeing them always makes my life better. So one of our main research topics is knitting. And we sort of started with the idea that knitting is coding. And for us, there's sort of many layers to this analogy. On one hand, there's sort of almost a language and a sort of grammar that comes out of knitting and the logic behind knitting. So if I were to take this dragon here and look at the pattern that makes it, there's sort of a code, there's all these sort of ASCII symbols that are indicating like specific topological arrangements of the needles and yarn to produce this pattern. And so I can look at that sort of grammar and encoding as sort of a type of code. This is an analogy that's really quite old. The jacquard loom was invented in like 1804. And the thing about this that's really fascinating is that this technology is the world's first binary technology. And so the way weaving works is you have a lot of threads running in one direction. And these are called the warp direction. And then with the other direction, you decide to go like over something or under something, over something, under something. And so every time you have this over or under crossing, that gives you an addressable bit of information. And so you can encode whether you want an overcrossing or an undercrossing in binary. And they do it using punch cards here. And that was the original technology. And then this was something that Charles Babbage and Ada Lovelace ended up using in the middle part of the 19th century as a way of thinking about mechanical computation. And basically this is the technology that was used in like the ENIAC and the first computers, like the ones that were the size of a room, before we were able to encode things in silicon and stuff like that. So the history of textiles encoding goes back like over 200 years. The other way we like to think about knitting and coding is that we like to think about these from the point of view of being able to program material properties. So the different combinations of stitches give us a lot of different mechanical results. And you've probably mostly heard me talk about this, so I'm going to skip kind of briefly through it to sort of basically tell you the main punchline, and we can talk about it more during a break if you would like to follow up. But the main idea is that these sort of stitches are basically pulling like a loop through another loop, and you can do that on the front of the fabric, or you can do it on the back of the fabric. And this is what people who knit sweaters and things like that do all the time. So this basic type of fabric we call stockinette. This is what you have in your t-shirts, like hoodies, socks, underwear. Like this is just like the most common fabric that we're all touching at all times. And we can kind of manipulate whether we're pulling loops through the back or the front in different ways. And these give very different mechanical properties. So the sort of inspiration for this project is because I'm a knitter, I know how knitters have used these things for centuries to generate different mechanical properties of their fabric. So I guess probably the most interesting one here is ribbing. And that's what makes up like cuffs and collars. And you might notice that like cuffs and collars have like a very different type of stretchability than like the overall fabric. And that's because they want to be able to like stretch over like a hand or your head and still kind of keep a close fit. And so basically we took inspiration from how materials were used in the real life to try to understand the math and the mechanics behind it. In addition to all of this, I've been really interested in working in mathematical art as well. So these are projects that are things that I guess I'm excited about. So the scarf I'm wearing is a project that came out of asking the question, what if you put a cellular automaton on a Mobius strip? And so someone posted this on Twitter, we wrote some code about it, and then manufactured the scarf based on it. We've done some projects in virtual reality, do a lot of things based on sort of building sculptures. This is a YouTube video that was, can you tie a knot by riding a closed path on the London Underground? So they tracked whether at stations, which line crosses over another one, and then we built a knot out of that. And I guess the last one is some mechanical motion. So we were also interested in that. So I do a lot of things, particularly with textiles. And I think textiles are an amazing way of looking at things like topology, in particular, because topology tends to have like a lot of flexibility to it. So we want to see what happens when we don't have like distances and angles. We want to be able to sort of pull in things as much as possible. So being able to make these sort of touchable objects means that people can very much like feel what the topology means in their hands. And I think that's something that is really powerful for trying to understand new ideas. So this is a quilt that is illustrating this thing called the clyde-Hordic curve. Here's another one that this showed up in Kotori Sensei's talk of what happens when you have this octagon and glue different sides together. So that was one of the questions she asked all of you. And then, so we do the gluing by using zippers, and we end up with like a two-handled torus. And you can sort of feel that by sticking your hands through in two different ways. This is a project that Lewis Campbell worked on. So basically this is looking at how we can add curvature to an object by using seams. So I'm gonna sort of skip through. Basically, we came up with a method of like bending seams in a coherent way. And this sort of adds sort of concentrated curvature distributed curvature to a system rather than sort of concentrated curvature that we use when we do sort of like angles and points. That gives us cones here. This gives us a smooth curve. And so he used these to make some scarves. So here's some versions of them, and you can see how sort of nicely that you can get it to drape around a neck by using like this distributed curvature method. I think I'm running out of time. Here's some views of virtual reality. This was our original project, but then we've sort of gone on to obviously vastly improve the graphics and make some newer virtual reality using some novel computational tools. And lastly, I'm gonna really quickly tell you about this project Math Malcolmy that we did. It's this room scale installation. The thing that I worked on, this has 24 mathematicians and artists who built this. And the part that I worked on a lot was the lighthouse tower that you can see, sort of the tall thing that's rotating around. And so this was based on the idea of being able to cut things out of sheet metal, and then by welding them together, you can get really complicated curves. So this is someone welding it together, and this is the sort of final project from a couple of angles. And I liked it so much that it is tattooed on my body. So this was quite fun. The other tattoo, if you'd like to learn more about it, there's a number file video on that tattoo. So you can check that out. I guess I also like designing fashion and jewelry and things like that. And sorry, I'm a little over time, but I guess this is the pendant I've been wearing, so you can also see that up close. But thank you so much for your attention, and I'd be happy to take any questions.